In this video, we will analyze the concepts of work and energy and how they are related. Think about this skier that is sliding across a slope. The slope is uniform and forces like friction, normal force, and gravitational force acting on the skier are constant. We could approach this problem and get information about the motion of the skier using Newton's laws. Newton's laws were easy to use in this case because the constancy of the forces. In the more general and realistic case, the slope will not be as uniform and it will have inclinations that vary from position to position. In this case, the normal force clearly will not be constant as the slider moves from one point to another. Friction might vary as well because friction depends on the normal force. Even if we can approach this problem using Newton's laws, we would need to use equations from calculus that involve integrals, derivatives, and differential equations. So that approach is beyond the purpose of this course. There is, however, a different approach that will save us and that will help us analyze problems with forces that vary with time and using only basic algebraic equations. The concepts that we will need are the concept of work and energy. And those are the two concepts we will discuss today. We will start by analyzing the concept of work. In our everyday use of the word work, we refer to an activity that demands from us some effort. In physics, however, work is defined in a way that is not always consistent with our empirical notion of work. In physics, we define work as the product of the force acting on an object times the displacement that the object experiences while the force is acting on it. Note that the force has an index in the form of two parallel lines. That indicates that not all the force contributes to the work, but only the force in the direction parallel to the displacement contributes to the work. Let's see what that means. Imagine a box that moves from the left side of the screen to the right side of the screen. So the displacement is indicated by the blue arrow. While the object is moving, the force F is acting on the object. Note that the force is not parallel to the displacement, but it has an angle with respect to it. We can always split in one component that is parallel to the displacement and a second component perpendicular to the displacement. The way work is defined says that only the component of the force that is parallel to the displacement contributes to do work. The component perpendicular to the displacement will not contribute to do work on the object. As a consequence of this, we can then forget about the component of the force that is perpendicular to the displacement. So let's analyze how can we calculate the component of the force parallel to the displacement when we know the magnitude of the force and the angle that the force makes with the direction of the displacement. Since we are trying to find the adjacent side of a right triangle, we can use the cosine of the angle to find the component of the force parallel to the displacement. This way, the work done by the force can be calculated as the magnitude of the force, the magnitude of the displacement, times the cosine of the angle between the force and the displacement. Now, work can have positive or negative sign. In general, when the displacement and the force point in opposite directions, the work will be negative. On the contrary, when the displacement and the force point in the same direction, the work will be positive. Let's now analyze what would be the sign of the work when the angle has an arbitrary value. Remember that work is defined as the magnitude of the force, which is a positive number because it's the magnitude of a vector, multiplied by the magnitude of the displacement, which is positive as well because magnitudes are always positive. So let's see what happens in all possible cases when the angle is between 0 and 180 degrees. Let's analyze the case when the displacement and the force make an angle between 0 and 90 degrees. In that case, the cosine of the angle phi will be a positive number. As a result of this, the work will be a positive number too. Next, let's analyze the case when the angle phi is somewhere between 90 and 180 degrees. In that case, the cosine of the angle will be a negative number, and the resulting work will be a negative number too. The last case is when the angle phi is exactly 90 degrees. In that case, the cosine of 90 degrees is exactly 0, and then the resulting work will be 0 as well. So let's move now to the concept of energy. Energy is a very difficult term to define in physics, but we can roughly say that energy is a measure of a system's ability to interact with and change its surroundings. We can say that changing the surroundings is an equivalent way to say that we do work in the surroundings. So, in a way, energy is a measure of how much work we can perform on objects. Think about the following. The sun radiates energy in the form of light that is absorbed by the plants, and the plants grow and accumulate chemical energy in their molecules. We then consume plants as food, and we take the energy from the plants, which we can use to perform our everyday activities. So we have energy because we can do work on other objects or modify the surroundings. Energy comes in a number of different forms. We can talk of kinetic energy, which is related to motion. We can talk as well of gravitational potential energy related to the gravitational force of the planets or the sun. We can as well have elastic or spring potential energy stored as tension in those objects, thermal energy, which is related to heat, chemical energy, which is in the chemical bonds of molecules, and nuclear energy, which is inside the nucleus of the atom. For the moment, we will consider only kinetic energy. Kinetic energy is related to the motion of the objects and can be calculated as the mass multiplied by the square of the velocity of the object multiplied by a factor of 1/2. What this means is that the kinetic energy increases with the velocity. So the objects moving faster will have more kinetic energy. However, kinetic energy increases with the mass as well. So more massive objects will have more kinetic energy when the velocities are equal. An analysis of the units reveals that the units of energy are joules, which are the same units that we found for work. And that reveals the connection between energy and work. That connection is expressed in the work-energy theorem. What this theorem says is that when one or more forces act on a system or an object and they do work on that object, the net work is equal to the change in kinetic energy of the object. What this means is that when we calculate the work done by each of the forces acting on the object, and then we add each of those amounts of work, the resulting work will always be transferred as energy in the object. And that energy will be in the form of kinetic energy. So you can see how the first term on the right side is just the kinetic energy at the final time. And the second term is just the kinetic energy at some initial time. So this is just the change in kinetic energy. So the change in kinetic energy is just equal to the net work. And that's it for this video lecture.